So I'm hearing no questions. That means I'm going to write some questions that look like this on the exam, and everyone's going to get them 100% right. Is that the deal we're going to make?
No, that's a good deal.
No, I really like that idea.
Practice them. I like that idea too. Practice them.
We will have a practice quiz. Well, lots of practice. What I'm going to do is a little bit different than I've done in the past. I'm going to go straight into heat engines today. And then we'll have a practice on, we'll have homework on Monday, and I really like it. It's 2 problems. And again, it works through these processes. And then what we'll do next week is we'll start to go over some of the theory that supports what we're doing, and then do a lot of practice looking forward towards the final. So I'm jumping right to the chase today on what the conclusion is on heat engines. We will then go back and fill in why some of these things are true. But the intent is we're just going to jump in right into how do we do it, and then next week we'll practice and go over a little bit why some of this stuff works. We have this very interesting math problem. It is relevant to today's lecture. So the question is, if we solve for P equals nRT, and we're going to assume we're going to go to some final state. And if we know that P's changing, B's changing, and C's changing, we're not going to say there's an isobaric, an isochoric, or an isothermal process. So possibly all 3 of those variables are changing. And we know that there's a relationship between P initial, P final, and B final. That's this weird relationship down here. How can we solve for B final if we know P initial? And then what I want to encourage you to do is do the math. So I'm going to say substitute for VI and substitute to solve for VI, substitute in here, and I'd recommend that you solve for V final here first, and then do the substitution. It makes it a little bit fun. So solve, in other words, I've got this backwards. Solve for V final, solve for V initial up here, substitute it, and what you get. I'm going to give you about 2 minutes to do that. What's that? Gamma is an exponent. While you're doing that, I will hand these out. But promise me if I hand them out that you'll focus at least a little on the lecture. Mary.
Good. You already know that you don't even know cheese, you know, so you're trying to figure out what, you know, not like waste time, so you figure out what you know. Like I've learned some don't know what I just learned. And that way when you get to the actual setting, you just like kind of memorize, remember everything, then you're like, okay, I already know what I need to know. So you can figure out what's
So that's pretty quick.
You would click on your fingers like that.
Well, actually, that's probably
Has everyone solved this? Oh, right. Take it out. Take it out.
Thank you.
Work backwards.
Yeah. I've lost that many.
Look at it. It's not gonna ruin it. Well, I'm gonna look at it after.
Oh wow, that's hey, oops.
All right. So the problems that really trouble people, real quick before we go to this, with it in this cyclotron, is the particle is accelerated everywhere. Right? It's accelerated in circular motion in the D's, so it's not speeding up, but it is changing direction. Between the D's, it's actually increasing speed, but not changing direction. So it is accelerating everywhere. It only speeds up, however, between the D's. Number one, if we look at Biot-Savart's law, directly in front of a particle, directly behind it, the magnetic field is 0. So there's no magnetic force. It creates a magnetic field, but the magnetic field is 0 in front of it and behind it. So if the two particles are heading directly towards each other, there's no magnetic force. There's a magnetic field created by both particles. There's an electric field created by both particles. But if they're heading directly towards each other, the only force that they exert on each other is an electric force. Then, for the most part, people did very well through problem 9. Problem 9, we were looking at a loop. And we're asking something about the current inside that loop. What do we know? We know Ampere's law, the closed loop integral of B naught dl equals mu naught times I. We know that the magnetic field's in a circle, so this becomes now a product of B times circumference of the circle equals mu times I, or I equals mu, 2 pi r B over mu naught. Now, that looks just like a wire. What happens when I want to know the current between the outer two? I saw this problem in the workbook. In the workbook, you were asked to integrate from here, then to here, then to there. And I started looking at the fields, and they decreased linearly. And I said, how does that happen? I said, well, let's make it a problem. All right. So inside the loop, there is a current. Actually, I had the current. The direction of the field is the opposite of the problem. There's definitely a current going into the board inside that loop. There's also a current going into that board inside the outer loop, if I look at the whole thing, and inside the loop for the inner loop, for this 4 centimeter loop and the 3 centimeter loop. But if you do the math, the current going into the loop inside the 3 centimeters loop is larger than the current going into the circle for the outer loop. So when you take the difference, the current between the two loops is actually coming back out at you. So if you redo this, this works for the inner loop, it looks for the outer loop, it works for the 3 centimeter loop. To find the current between the 4 and the 3 centimeter loop, you can take the difference between those two. Now somebody, a couple people must be in Calc 3 because they did that loop, which also works. So they created a loop where they went all the way around the inner loop in one direction, in the opposite direction of the magnetic field, then jumped across and made that loop. That also works. It's a single loop composed of 2 integrals, and then you make these parts of the path close enough so that they overlap. Or the fact that they don't overlap is insignificant. Any questions about that problem? So the interesting thing is the current's going in the middle of that situation, and it's coming back out on the outside. If you go one more loop farther, and the magnetic field is now 0, what's the net current inside that loop? 0, the magnetic field. Then everything else worked pretty well. People did really, really well on 12. 13, a lot of people didn't recognize that that was circular motion, because that was cyclotron motion. So we had to sum our forces. Our force was, our force is Q, B cross B, but B and B were perpendicular, so the magnitude of the force was Q, B, B. That's equal to mass acceleration is equal to mv squared over r. We know everything but B, and we can solve for B again. We know everything except for Q. At that point, I can solve for Q. Any other questions about the test? Bonus. Number 4. Oh, what happens when the coil is moved to the right? At that point in time, the North Pole, there's field coming out of the North Pole. As we move the coil to the right, the flux through that coil is decreasing. The current needs to be induced in a way to maintain that flux. The current will be induced from right to left, from left to right out of the ammeter. And that's to keep the flux, to maintain the flux. We're moving the coil away from the magnet. So by Lenz's law, we want the current to keep. Other questions?
You talk about the bonus problem.
Okay, the bonus problem. Remember, the bonus problem you actually saw in your workbook. Remember this problem here where you had the dotted line and the magnetic field was going in a uniform direction on one side and it was going the uniform direction on the other side? And then when we used Ampere's law, we took a loop here. How much current is going through that box?
0.
This one down here.
0.
But when we did the one going across that dashed line, we found that there was a current. So there's a sheet of current moving out. Well, it depends on what the, actually in this case, the sheet of current is moving into the board. Right? All I did is turn that sideways. So take and look down the y-axis from the bonus problem. I think it's the y-axis, isn't it? Look down the y-axis, and if we have the y-axis pointing straight out at you, this is what we see. We see a sheet of current coming towards us. We choose an arbitrary length L, and we integrate around that path, and we'll find that we'll have, let's do the 4 parts. The top will be B times L plus 0, and then again plus B times L plus 0 equals the current inside, which is L times, did I give a current density? Times 2 amps per meter. The L's cancel. We have 2B equals 2 amps per meter, or B equals 1 amp per meter. So it really was just the bonus problem. Now this is also the top of your solenoid. If you think about it, if you think of a very large solenoid, this is the top of the solenoid with the current coming out at you. Imagine that we do another large sheet down here, with current going the opposite direction. What's going to happen? It's going to create magnetic fields. Let's see, on the top above this, the field will be going into the left. If this current density is the same as that current density, we'll get twice the field in here. What happens to the magnetic field out here? It cancels. What happens to the magnetic field out here? It cancels. Doesn't this look an awful lot like a capacitor? So an inductor, if you look at a very large conductor, is 2 sheets. It is a very direct analog to a capacitor in terms of approach. So the connection between capacitors and inductors is a lot stronger. We can store energy in a magnetic field in an inductor. We can store energy in the electric field in a capacitor. So it's kind of a fun little problem. No one recognized that it was the same problem as the homework problem. You just had to look down that sheet. I kind of hinted when we talked about that what is this? This is a sheet of current. And I thought to myself, that would be a great bonus problem. I was hoping that it would click with some of you. All right. Any other questions about the exam? All right, let's put it away. Focus. That is a hard exam. When we're talking electric fields, magnetic fields, that is non-trivial. You guys have come a long ways this semester from starting out with, actually this year, when you think about it, we started out with kinematics, we talked about how things move, we talked about forces, Newton's law, why things move. Then we got to fields. Fields are really something, all right? We've come somewhere in this class. We've covered a lot of experience. Well, we've now come to ideal gas laws, which I think you're comfortable with. The problems are a lot more straightforward. This is the hardest math we're going to have to deal with, is these exponentials. So let's go through it right now. Let's see if we can remind ourselves of how to deal with these exponentials. This is what we need for our adiabatic processes. So when we talked about calculating the work for isochoric, that's probably the best, right? What's the work under in an isochoric process? 0. Bingo, I can do that. An isobaric process. P times our change in volume. All right. So that's pretty straightforward. It's an isothermal for us, so our work is, we have to use a log, natural log, but it's still not too terrible. And then with adiabats, we have to use exponentials. This is where it gets a little bit dicey. So what do we do here? So let's just go ahead and solve for V final in this equation down here. We have P initial, V initial to the gamma equals P final times V final to the gamma. And I want to solve for P final. So let's first divide both sides by P final. Rearrange it a little bit. P final to the gamma equals P initial divided by P final times V initial to the gamma. Now what do we do? Can we divide? You have to take the 1 over gamma root of both sides. How many people are comfortable with that? Try review your math so that you're comfortable with how you deal with these fractional exponents. What's the square root of 4? We could write it like that, but can't we also write it as 4 to the 1/2? 2 squared, square root of 2 squared is equal to 2 squared to the 1/2. We take the product of the exponents, that's equal to 2 over 2, 2. If we're really proper. Good remembering? No. Now, let's finish this. So let's go back to our initial, solve for V initial. V initial equals nRT over P initial. Now we can substitute that in for V initial here. Substituting that into there, bring it over here, we'll have V final equals P initial over P final times nRT over, there's 1 over gamma, initial. So now we have the P initial to the 1 over gamma divided by P initial. What do we do with that? We subtract 1. That will be P initial to the 1 over gamma minus 1 over P final to the 1 over gamma times nR. For a lot of us, this is algebra we haven't done for a while. We haven't done it fresh enough.
So is this, independent of temperature change?
So, the question is this an isothermal process? And the answer is no. What we're talking about here is an adiabatic process. And so for different gases, there'll be different gammas. And to solve our gas laws, we'll want to be able to do math like this. There'll be some equations that simplify things, but to really understand what's happening in adiabat, we need to be very comfortable. What I'll tell you is for an adiabatic process, this holds true.
And what exactly does gamma represent?
We will get to that.
Okay.
So what I'm doing that's a little bit backwards this time is last time I defined what gamma is. It is, and you can understand that in terms of statistical mechanics. It has a very significant, there's very significant.
Sure.
It represents something is what I'm trying to say.
Mm-hmm.
But we're gonna hold off.
Can't we then just take B final, and say it's equal to what, nRT or nRT final over P final, and just remove volume from the equation altogether, and just put it in terms of pressures and temperatures?
Well, kind of the situation I'm creating here is that we have some process, and what I don't know is the final volume. And if that were true, then we'd have to do it. But depending on what we're solving, we may have to do something different. But perhaps, maybe I can understand your question. So I was assuming we wanted to find B.
Oh, okay.
Yes, there will be other cases where we want to do, solve for different things from those. But the point is, how many of you feel absolutely 100% confident with this? How many say, yeah, I can kind of follow it, but it's a bit dusty? Some people say that's absolute witchcraft.
Absolutely.
So, most people, I think, are in the position I expected, which is, it's been a while since we've looked at this. And that, it's meant to be there so you can, get comfortable. All right. So, the bottom line of this is, we should know this math, refresh it, be good at it. Right. Now, in lab, I've told everybody that temperature, heat, goes from hot objects to cold objects. And there's something that really bothered me when I first started studying thermal. To me, when something was heated, it was hotter, there was more heat in it. That's the way I thought about things. In terms of thermal, that will guarantee that you get confused. That is not the way to think. Right? It is the way we talk about things in normal language. But it's, again, there are very precise definitions. If something has a higher temperature, does that have anything to do with heat? Not necessarily. It may have nothing to do with heat. We know from our first law of thermal that our change in our thermal energy is equal to Q plus work, or what this is work done on the system. Let's make that a W rather than omega. Can this be zero and have thermal change? Yes. We can do, we rub our hands together. Do our hands get warmer? There's not heat involved. That's work increasing the thermal energy. So, you rub your hands together, in the view of physicists, you are not creating heat. You're creating thermal energy. Right? Please, if the temperature increases, has there been heat? Not necessarily. If it could have been, maybe someone put a flame under it, in which case, yes, there was heat because energy transferred from a hotter object to a lower temperature object. I emphasize, heat is energy transfer. Right? From a hot object to a cold object. If there's work, then that is work. Energy is transferred by work. If we're rubbing, there's motion, there's forces, there's work. That work is creating thermal energy. Now, our second law of thermal, I will tell you, tells us that one of the parts of it is that temperature, two objects, temperature measures the thermal energy. If we have two objects at different temperatures, they're adjacent to each other, energy transfers from the hotter object to the colder object, from the higher temperature object. That is heat, that energy transfer. That will happen spontaneously. Energy will not spontaneously change from the transfer from the cold object to the hot object. That's very good. Now, what does your refrigerator do?
Takes the heat away.
It cools down the inside of the refrigerator, right? So somehow heat is transferring out of your refrigerator and going into the warmer room. Is that a violation of the second law of thermal? That's what all there was to the story. You just put that box there, and heat moved from the inside to the outside. That would definitely be a violation of the. It would also make you really happy because it wouldn't be plugged into the wall, and you wouldn't be paying a Vista, right, or whoever the local utility is. So you are plugging that refrigerator into the wall. Why? There's a compressor in the back. There's some work being done to make that happen. And what I'll tell you is the secret is there are coils in the back of your refrigerator that are hotter than the room. And the heat goes from those hotter than the room coils into your room. And there's also coils inside the refrigerator that are colder than you want your refrigerator to be. And heat goes from the inside of the refrigerator to those coils. Now the mystery is, how do those coils become colder than the refrigerator in the back? And how do the ones that are inside, and how do the coils in the back become hotter than the room? I'll tell you where there's heat in the refrigerator. Those are the two places there's coils. There are coils in the back that are colder than the refrigerator. So there's heat that goes from the inside to those coils. And then there's coils in the back. They get really dusty. By the way, if you want to pay Vista less money or your local utility, every once in a while pull your refrigerator out, find all the weird stuff underneath it, clean it out, and then dust off the coils in the back, and then your refrigerator will be a little more efficient. But how do we make those coils hotter and colder? Now engines, so refrigerators are a little bit of a mystery because they appear from the outside to violate the second law, but I just promised you that they don't. Because these coils. We have to figure out how the coils work, but we'll figure that out when we have the whole thing done. Then we have engines. What does your car engine do? You go to this Shell, hopefully, actually you can't do that in Spokane anymore, and get gasoline. Pay the gas station money, and then when you run your car, the gasoline burns in the pistons, creates heat. Right? You have chemical energy that creates a higher temperature, and then that will expand the gas in the cylinders. That turns into mechanical energy. So in that case, you are definitely adding heat by buying some kind of chemical fuel, and unless you have a Volt or Tesla. But in the old cars, this used to be simple. If you have a gasoline engine or a diesel engine, you're burning your fuel, there's heat created, that heat is turned into mechanical energy. You buy chemical energy, you turn it into work. So we're going, for engines, we're going to somehow acquire energy, and we're going to turn it into work. So what we want to do is now start to explore how that works. We're going to go back to our friend, the piston. I was going to have a quiz, but we're not behind. And we'll put it off, I think, towards Monday if we don't keep going. Again, heat is energy. Energy what? Transfer. So we have to have a hot object and a cold object to have energy. Now in an isothermal process, that temperature difference is really, really small. It's not. And heat always moves from the higher temperature object to the lower. And again, we've kind of got the secret out in the refrigerator. My daughter did a transport class in for energy transport. Did you guys take transport here? Chemistry? I took a whole class on transport of heat and fluids. They had bars and labs, and they had monitors along. They looked at this not in a static situation, but what happens when it's you just first started. They had temperature monitors over the whole thing, and then they measured temperature over time, and then they had to model all that. It's actually a pretty interesting class. But for us, all we need to know is that if we have a high temperature and a low temperature, there will be a transfer of energy. Microscopically, these molecules become more energetic, they collide with these objects, they become progressively less energetic, and then energy gets drawn out into the ice. So if we have heat transfer in the positive direction and the negative direction, when this becomes an equilibrium, there's energy transfer along the bar. This actually, when you model them in steady state, it's not like a resistor. This temperature is like your positive voltage, this temperature is like a lower voltage, and then you describe the material like resistance, and then you can figure out the inner heat flow. And not surprisingly, the bigger, the wider the bar, the lower the thermal resistance, the thinner the bar and longer the bar, the higher the thermal resistance. We're going to define a new thing, an energy reservoir. Remember the hot bath we talked about, or the cold bath? That is an energy reservoir. Energy reservoirs are another wonderful model. We can draw as much heat as we want out of an energy reservoir, and the temperature will not change. This is an object. We got an energy reservoir. We can melt as much ice as we want in that energy reservoir. The heat will come in, melt the ice. It doesn't change temperature. So again, it's a convenience that allows us to have isothermal processes. So what we're doing is we're getting things set up so that we can start to analyze refrigerators and heat engines. With all these definitions and our warm-up in math, we are now ready to talk about heat engines. Energy will be extracted as work, so there will be positive work out down by our engine. That's what we're paying the fuel for. When you go to the gas station and buy gasoline, you're paying for chemical energy in order that you can get work done. You want to be able to drive to where you want to go. We will study closed cycle heat engines. We're not going to change the number of moles inside our gas. We won't have exactly the model inside an engine, because an engine, there's fuel going in, there's air going in, there's exhaust going out. We're going to treat everything as closed cycle, but it's adequate to do a lot of analysis and really understand what we need to understand. In a closed cycle heat engine, we have some process that gets repeated again and again and again. How many people have tachometers in their car? When you're kind of racing along, what's your speed? Maybe 4,000 or 5,000 RPMs?
That one's driving fast.
Or faster, right? Well, you think that 6,000 RPMs. That's 6,000 times a minute. That's 100 times a second. These cycles get repeated very, very quickly. Well, remember, they're quasi-static. Now, the thermal, we will draw these cycles on our PV diagrams. A simple cycle might have isocaloric and isobaric process and maybe an isothermal process. And we go around and around and around. In this cycle. And I'm saying the thermal energy at any point, let's just arbitrarily call these 1, 2, 3, back to 1. I'm saying at 2, the thermal energy is always the same. Why? Why would the thermal energy be the same at any point on that cycle? We're repeating it again and again and again. If it's Austin hurrying home, it might be 100 times a second. Why is the thermal energy at 2 the same all the time? Every time it goes through that cycle. How do we determine the thermal energy in a process? Let's say going from 1 to 2. Is that an increase or decrease in thermal energy? Could have been the quiz question. From 1 to 2. What's staying constant from 1 to 2? Volume. So it's what type of process? Isochoric. Are we doing work? I'm going to change back to our this form. So now we're doing work out, so I put the negative sign. The work out is 0. Do we know anything about the temperature? Temperature is increasing. What does that tell us? Does that tell us something about the heat? Not necessarily. In this case, it will. But what does it tell us for sure? It tells us the thermal energy. Has the thermal energy gone up or down? Up. Because the temperature's gone up. What's the temperature at 2? The number of moles hasn't changed. The pressure and the volume are the same every time we get to 2. Now, what does that tell us about the temperature? Every single time we get to 2 in the cycle. It's the same. So the thermal energy is the same every time we get to 2. The temperature is the same every time we get to 2. So in this case, E thermal is positive, work 0. Q must also be positive. Now, the work done from 2 to 3. How do we find it? The area under this curve. Since we're looking at work out, is that positive work or negative work? Positive. So, the area under the curve, that would be this whole area right down here, wouldn't it? What about the work done from 3 back to 1? Is the work done by the system positive or negative? It's negative. Right. Now, we're back to 1. What is our change in thermal energy be over that entire cycle? If we add up the thermal energy here, plus the thermal energy here, plus the thermal energy here. 0. So if we look at this whole cycle, our equation becomes this. Or more interestingly, work out equals the Q for the cycle. This is what we get. This is what we're paying for. And what is the work graphically? It's the area inside the cycle. Because we're going to take the work across the top, going from left to right, minus the work across the bottom, going from right to left. So this is pretty cool. We can look at this and we can figure out what the amount of work is in that cycle. So as we design cycles, the work out is equal to the area. So we want to make this area as big as humanly possible, don't we? So that doesn't seem so hard. That we're designing engines. All we have to do is make that work area. We put a Q in, we get work out, and we get a working engine. Now here's the sad part. answered that. Now, I used the positive convention here, but I will go to the other convention. So then we change to workout, and workout is equal to our heat in. We will draw our heat engines as there's some source of heat. Inside of a car engine, that source of heat will be the temperature of the piston. And the cold reservoir is where that energy goes. Well, where does that energy go in your car? Right? When it leaves, it's going out the exhaust. So this would be the temperature of the combustion in your engine. This would be the temperature of your exhaust. Now it says cold reservoir. Your exhaust isn't exactly cold, but that is the temperature that the gas is leaving the engine. So if we measure the amount of heat QH going into the system, the QH hot is going into the system, then Q cold is coming out of the system. So if this was an isotherm, we'd have heat going in during this cycle. We'd have no heat during this cycle because it's an isothermic process. Then we'd have heat coming out of that process. We can find out that our workout will be equal to QH, the Q going in from the hot side, minus the Q leaving to the cold reservoir. And that will be equal to the work done by our engine. So we add some heat in, that's what we're buying. We lose some because there's some heat in the exhaust. There's some transfer of energy to the environment. And we get work out. We pay for this. We're trying to get, this is what we're paying for work. The efficiency of this will be the work out divided by QH. What we get for what we paid for. The second law, and I'll state this without proof, is that the efficiency of our engine, the work out divided by the heat we're getting, is equal to or less than 1 minus the temperature of your cold reservoir divided by the temperature of your hot reservoir. Now let's think about this really quick. Let's say the exhaust of your car is 400 Kelvin. These need to be absolute temperatures. And your combustion temperature is 600 Kelvin. 400 divided by 600 is what? 2/3. Your maximum efficiency is 1 minus 2/3 or 1/3. So you're paying for, if you had a perfect engine that had exhaust of 400 degrees and its combustion temperature was 600 degrees, if it were perfect, there were no losses, there were no friction, the engines worked absolutely perfectly, your maximum efficiency would be 33%. So for every $3 you spend, you're only using $1 of that energy to actually make your car go. Real cars are less efficient than that. That means 2/3 of the heat is coming out of the exhaust. See why I don't like the second law of thermal? Evan.
What is it in reality?
What's that?
What would it be in reality for most cars?
It's about 25% on average in the country. Now the CAFE standards are trying to raise that, but there's a limit. I mean, then sometimes I look at the numbers that they put in the future goals, right? So that they legislate what the laws are, and I think it ain't going to happen. They just physically, it's not going to. So then what they do is they start to modify things. They make the cars smaller one way. But then people don't like the small cars because you have people driving SUVs and you're terrified that if you get run over by an SUV, you get killed. But the other thing they do is they start cheating. They'll modify the laws. But there's a certain point in time where if we're going to have combustion engines, we have to have a way to increase the temperature of combustion tremendously, which means it's evolution of materials, or we just can't get there. It's not going to happen. We're done at 5-2.
Yeah.
People are getting restless.
People have an exam. We can stop here. We'll go over examples on Monday. Please read over the textbook on this heat engine stuff. We will do a quiz on what's going to be the process.